again, everybody. So now we're going to take a look at the math behind parametric applications of projectile motion. Here are the two equations that we came up with in the last video. X is equal to initial velocity times cosine theta t. Y is equal to negative 1/2 g, which is the acceleration due to gravity, t squared plus v sub 0 sine theta t plus h sub 0, the initial height. You'll notice that the coefficients in front of t involve the trigonometry cosine theta and sine theta for x and y respectively. What this is doing is it's taking that initial velocity and distributing it in the correct proportion to the horizontal and vertical distance, depending on how steep that angle is. The steeper it is, the more it has an impact on the vertical component. The more horizontal it is, the more it has an impact on the horizontal component. So this graph will end up having an initial height here, and it'll come across like this, where these are the x and y values. The t is kind of hidden. T equals 0 is that first value, and t equals 1 might be here, t equals 2 might be here. So each individual t value kind of has its own corresponding x and y component that goes with it. Let's take a look at an actual example here. So we're going to create a set of parametric equations based on this given information. A basketball is thrown with a certain height, initial velocity, and a launch angle. Let's first identify these numbers for what variables they represent. From a height of 7 feet, that is our initial height. Initial velocity of 25 feet, that is our v sub 0. And a launch angle of 65 degrees, that is our theta value. Putting it together, x is equal to v sub 0, 25, times cosine theta, cosine of 65, times t. I'm just going to do capital T just so it's not confused with a plus sign. Y is equal to, because we're dealing with feet here, that means we are going to use the 32 feet per second for g. That makes this the familiar negative 16 t squared plus 25 sine of 65t plus h sub 0, which is 7. And those are the parametric equations for this problem. Now the second part B here, the ball is shot at a hoop that is 10 feet high and it's made perfectly. So if we think about this starting at 7 feet, it would go up in the air, come back down, and then it's going to hit 10 feet somewhere on the return. So our job now is to figure out what that time is. So if I think about 10 feet high, that is a y component. So I'm going to set 10 equal to the y equation. Subtract 10 to both sides. 22 sine 65 is 22.66. And we end up with this quadratic. It will not factor, so we have to use quadratic formula. The quadratic formula I've already put inside the calculator. I get these two answers here, 0.1478 and 1.268. Because we're looking for the way down, we're going to choose the bigger number, 1.268. So that's how many seconds it takes to go from 7 up in the air past 10, then back down again to 10 again. What we want to find out now is how far away horizontally this person was. So what we're going to do is we're just going to take this 1.268 and plug it into the x component equation. So x equals 25 cosine 65 times 1.268. Let's do that math out. .4 feet away. And that's the answer to that question. One more thing to show you here has to do with graphing. So if you you can put this in your graphing calculator, the set of equations here. If you go to mode and you switch it to parametric mode, so go function then PAR for parametric. Now when you go into y equals, you will notice that all of these values now have x and y in them instead of just y. So we're going to put in 25 cosine 65 t for the x component and the y component, negative 16 t squared plus 25 sine 65 t plus 7. When I look at the window here, because we want to get the right graph, you want to think about what these all mean. So 0 is the beginning step, t max 6.28. The t step is 0.1, that's just going to be how often the calculator gets points, that's fine. The x min of negative 10, I'm going to make that negative 2 just so I can see the x-axis. And we had 13.4 feet here, so I'm going to say the x max is somewhere around, I don't know, 25 or so. We'll go by 5s there. The y min, negative, let's go to negative 5. The height, it probably doesn't get above 20 feet high. It is a basketball. And the y scale 1. So this should be set up now. And if we go to graph, there is the parametric model, height, horizontal distance. And if you go to calc, you can plug in any t value, like t equals 1. You can find out both the horizontal and vertical distance that this ball has traveled after 1 second. Okay, good luck with the rest of the assignment.